I see some of you are here early. Can those who are here already say hi? Yeah, I'm gonna need a small favor from you guys for a little experiment. Oh, hi. Hi, okay. So quite a few are there. Yeah, so this experiment is this. I want to know a little bit more about the delay from me speaking something to the time you finally hear it. Okay, so what I'm gonna do is I'm gonna type 1, 2, 3, 4, and you let me know. Okay, until what time you hear until which number. So when I'm counting 1, 2, 3, 4, I'm gonna also type it in on chat room. So let me know when you hear me saying 1, what is the number you see on the channel? All right. Okay. So here it goes. 1. Oops. Do it again. Sorry. I need to hit the enter here. So do it again. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I guess that's about 5 seconds. No delay? Wow. Really? So you're seeing, Calvin, you're seeing the numbers as soon as you are hearing me saying the exact number. Very little delay. Interesting. So I guess the delay is user dependent. So it's not exactly all of you experiencing something like 5-second delay. I see that some of you say no delay, some of you say 2 seconds. So chances high that those who don't see any delay, you are probably tuning in from within the dorm or somewhere around campus. So yeah, I actually made some change again last night because I really like the chat being a little bit more in sync with the video, so that when you type something, I know exactly what you are referring to. Sometimes it's a little bit hard. So I changed from using wireless network to wired network. So my teaching computer here is now connected directly to a gigabit Ethernet through department's powerful 10 gigabits switch. I think department's switch might be even higher end, okay, faster than 10 gigabits. Oh, hi. Good morning, all. Yeah, so the Google Meet window is replaced by Gopher. That indicates, sorry, not yet. So you guys cannot yet call in. Okay, I promise you, perhaps next Wednesday we can try doing that. Okay, so the timing for you guys to call in is anytime, in fact. But I would say typically you guys call in while we start quizzing. Okay, so when I give out the quiz and you guys want to talk about your solution instead. Another window of opportunity is probably when we do Q&A. All right, so let's go over the necessary information for you to see. And you probably see that in the announcement, there's a certain pattern, okay, for every lecture and for every Thursday. So bullet number 1 here is always the link to the live lecture, which is trivial given that you guys are already here. The second bullet on Thursday is always, hey, what are the assignments due and what time, what day? You see that this week we do have quiz 2 to 4 and PA1 due. And therefore you see there are 2 more quizzes today. Okay, so one for the first hour and another one for the second hour. And let's move on to the topics. Okay, and this is only the first part of the topic. Let's move on and finish all the access network technologies. The third one is very popular these days. Fiber to the home. This is the third access net technology. Unlike the previous 2, where we kind of exploit certain existing infrastructure, telephone network or cable TV network, this one here builds its own network. And because the cable are all optic fibers, so it's called a optic network. And it's essentially the internet service providers, if they want to allow users to access internet using FTTH, they will have to go out there and build these optic links into the civil infrastructure. So there are physical contact, okay, through some cables between the central office to home. And so you see in this example, it's very clean, between the central office to each household, just optic cable, optic cable. The only slight complication and boxes that are a little unfamiliar to you are these. First, optical line terminal, optical line terminal. So this is a dummy device. What it does is just to collect signal and then convert them into digital bits. Okay, so that these internet data can go on natively through the edge router and out to the internet. Now, what's a little bit more interesting is this box, the optic splitter. We've seen this term, splitter, the third time. Yeah, at the physical level, these splitters are essentially the forwarders or the switchers. Okay, so signals gets forwarded to the right destination at this point. And signal gets multiplexed also so that they can go on further upstream. Okay, so splitter plays the role of demultiplexing signals so that it reaches a particular household, or multiplexing signals so that it goes to the central office. So its role is a little bit like the routers or switches at the core of the internet. So optic splitter here is a very important device for the optical network. In this example, we see there's only one level of it. In practice, there could be multiple levels, so that you could have a regional optical splitter, and then you could have another splitter here inside the building in case there are multiple households in your building, okay, also subscribing to the optical service. Now, these splitters, depending on the mechanism that's running in it, okay, depending on the design, could work differently. Okay, so 2 typical architecture for these splitters are these, PON and AON. So passive optical network. What it meant is that what's being done here is very straightforward. You just have mirrors so that you can reflect signals so that they go on the right direction to the destination. There's no signal amplification. But if you use active optic network splitter, yeah, these signals get splitted and amplified before they get passed on further. That is very necessary in case there are multiple levels of splitters along the way. As a signal, as it travels longer distance, even though it's optic signal, it still decay. Okay. Now, in FTTH, yeah, the downstream or upstream bandwidth vary, but essentially the maximum capacity is much higher than the cable modem network, than the DSL network. Okay. In Taipei, very typical, you subscribe to services that's downlink 100 megabits per second, uplink 40 megabits per second. Okay. If you have special need, for example, if you are hosting web servers, then you might subscribe to 100 megabits per second downlink and 100 megabits per second uplink as well. Okay, so it can be symmetric, it can also be asymmetric in terms of the bandwidth in going in different directions. So essentially much higher rates, and it really depends on how much you can afford. Right? And nowadays these fibers can also carry telephone or television services. Okay, think about video on demand. So that is to carry TV programs through FTTH. And digital phone, okay, IP phones are one example. The trend is going towards that's just move to FTTH and then abandon the older legacy technology such as telephone, such as cable TV. So all content, including data, are transmitted over the one and only internet. One ring to rule them all. How do you like that? Yeah, so we are all converging to using fiber for residential access. Now for institutions, companies, or for example NTU, we do Ethernet. The fourth network access technology is Ethernet. Now this is something that we're very familiar with. All we need to do is to purchase one of these Ethernet switches, connecting our computer through the Ethernet cable to it, and this guy is connected to the edge router. Then data can go out and in from the internet. Such a network access is typically used in companies and universities, okay, as they have direct access to the edge router. For households, we usually don't have access directly to the ISP's edge routers, okay? So even though you're trying to connect your end systems through Ethernet cable to a switch, but that doesn't mean your access network is that Ethernet you're using. Be careful. Now, the rate these Ethernet switch is operating goes from 10 megabits per second 10 years ago all the way to nowadays 10 gigabits per second. But I think typically people use an Ethernet switch at this speed, 1 gigabits per second. And nowadays it's actually dedicated upstream 1 gigabits per second and downstream also 1 gigabits per second. 10 gigabits per second Ethernet is a little bit limited, and only those companies who are, for example, hosting a lot of data, then they need 10 gigabits per second Ethernet, particularly video providers. All right, so the 1 gigabits per second switch costs about $500, $700 today in NT dollars. But 10 gigabits per second switch, depending on how many ports you need, can go up high as 10K NT dollars. Okay, so that's the price difference. And that's why typical households or small departments are still using 1 gigabit per second switches. Now the last one is wireless access, and this is for us moving around or going somewhere that's not home, that's not office, where we don't have wire connection. This is the last access technology. It's called the wireless access. That's just how I refer to both of these wireless access technologies in a general term. Okay. The common characteristic is that all the devices, okay, on the same channel will share access. So the way it works is this. Devices sending wireless signals. It's picked up by the wireless base station and then passed on to the edge server and then further on to the internet, and vice versa. So these base stations, in the context of Wi-Fi in particular, are also called the access points. Now a little bit more about Wi-Fi. AL2.11b or G. This is actually a pretty old standard. I'm pretty sure that all of us are using AL2.11 at least N. Okay, so that's Wi-Fi generation 4 in another way. The bandwidth with Wi-Fi generation 4 is already close to 400 megabits per second. Okay, and the frequency band is no longer just 2.4 gigahertz, but also the 5 gigahertz band. Okay, that's why when you purchase a new Wi-Fi AP, you see that, hey, a lot of times when you set it up, you see 2 channels, one for 2.4 gigahertz, the other for the 5 gigahertz. The next major generation is Wi-Fi 6, which operates also on both 2.4 and 5 gigahertz for backward compatibility in case you're still running AL2.11b or G. For Wi-Fi 6, the bandwidth actually go up this high, 900 and plus megabits per second. Really nice. I think in the next generation, that's called the AL2.11ad. Yeah. For this version of Wi-Fi, it's gonna operate at this frequency band, 60 gigahertz. It's super high frequency, super high data rate. In fact, 5G is also aiming at this frequency. So bandwidth is going to be a lot higher, but you see also that the transmission is very directional, a little bit sensitive to the antenna design, okay, and very sensitive in case there's mobility. All right. Wi-Fi, interesting development there, AL2.11ad. The last one, okay, wide area wireless access actually meant, so 1 megabits per second, this is for 3G. Okay, for 4G we get slightly more than 1, sometimes go a few megabits per second. With 5G you get easily tens of megabits per second and sometimes very close to 100, but only downlink. I have not yet seen any sort of measurements about 5G uplink bandwidth. It would be very interesting to know if you find any. Okay. But although these bandwidths we're talking about, downlink, uplink, it's increasingly higher and higher even for wireless access. But be very careful. As opposed to Ethernet, as opposed to optic, wireless is, after all, shared access. So these 400, 600, 900 or close to tens of megabits per second bandwidths are shared among all the users. And nowadays we are probably connected to the network more through wireless access network, okay, than the wired one. So do you connect to the internet more through wireless means or the wire means? Okay, let me know. Type it up on the YouTube chat. Next video, relatively short, just to sum everything up about the access network technologies. To sum things up, we've talked about 5 access networks: DSL, cable modem, and the very powerful FTTH, the optical network, to allow all the data, not just text-based, but audio-video data, to traverse. And it's replacing the traditional phone network, replacing the traditional cable TV network. We also talk about Ethernet access and the very, very popular wireless access. Now, all these 5 are access network technologies. These 3 definitely use a lot more for residential access. These 2 definitely use a lot more for institutional and mobile access. But nowadays, in a household, as the demand of using internet is on the rise and there are a lot more end systems are connected to the internet at home, having just one particular access network to enable multiple machines to go online at the same time is really challenging. So we have a hybrid access network in a way. In this example I'm showing, this is very typical home setting. Cable modem here, is to access to the internet for the household entirely. But after the cable modem, we have what? An Ethernet switch here, okay, which is also called a router, which also runs the firewall functionality. This guy here would allow, for example, these PCs to connect through Ethernet cable to it. Yeah, these PCs are accessing internet using Ethernet switches. And the switch here can also connect to a Wi-Fi AP, and so that these laptops are accessing Ethernet through Wi-Fi. So in just this example, you have devices accessing the internet through different access net technologies. And be a little bit careful when I ask what is the access network for a particular computer. It can be relative, right? So this guy here is through Wi-Fi, this guy here is through Ethernet. But if I ask, how is this household accessing the internet? Yeah, the access network used by the household entirely is the cable modem. So that was the first part for today. And now we move on a little bit. It's still about access network, but it's about the cables medium being used. Here we're going to switch gear a little bit, but still about access network technologies. And so far, if you paid attention, each of these access net technologies operates on some sort of mechanism or protocols. They also operate with assumption on there's a companion physical media. This is important, just like the protocols are important to achieve a certain expected performance, typically achieving a really high bandwidth. Okay. Now, so let's go over these physical medias that work side by side with each of these access technologies. Now first, let's define some terms. Bit. These bits are propagated between the transmitter and the receiver. And between the transmitter and the receiver, whatever the media is called a physical link. And these links can be wired. There's a special term called guided media for it. If it's wireless link, then it's unguided media, meaning that the signal might just go propagating omnidirectional everywhere. Okay. As opposed to guided media, there's usually a copper wire or an optic fiber that the signal kind of just follow and being guided to travel through the physical media. Now, there are four kinds of physical medias we'll be talking about. First is twisted pair, and this is one of the commonly used cable for Ethernet. Cat5, this is very old for Ethernet that's 10 years ago. Nowadays, I think we're still using a lot of Cat5 cables, which supports up to 100 megabits per second and might be reasonably okay for 1 gigabit Ethernet. But if you purchase a 10 gigabits per second switch for intensive use, make sure you get these cables, Cat6, particularly 6A. This will allow you to have physical transmission bandwidth up to 10 gigabits per second. Just, by the way, it doesn't make sense to buy a really high-speed switch and the cable limits the speed. Okay. Next in line is coaxial cable. And this picture shows pretty much the structure of such a coaxial cable. What it meant by coaxial is that they have two layers, concentric, and these two layers of coppers allow you to send signals. And because having two layers, it kind of allow the modulator, demodulators to easily cancel out the noises. And so data goes bidirectional on such a cable. A very primitive form of this coaxial cable was used by the legacy Ethernet. Yeah, by baseband it meant that the bandwidth is really, really small. very low rate transmission, and it doesn't exist anymore. But then cable network picks it up a bit, enhance it somehow so that they can send multiple video programs over it, allowing multiple channels on the cable. And the cable exactly used by the cable network is HFC, the hybrid fiber copper cable. Oops. And the third is the fiber cable. Okay, so this is entirely glass-based fiber, and the bits are being sent as pulses, okay, like that. It works in a very high speed. You can go up to hundreds of gigabits per second. These high-speed fibers are oftentimes used by OSO, the internet backbone, where lots of data are being exchanged. It's also used by the data centers, where there are always high volume data that needs to be stored or retrieved. These fibers, as we heard, FTTH, some of them slightly lower end is used for residential access as well. And they are very high speed, partly because it's very low error rate, because they are more resilient to white noises, background EM noises. The last media is the radio link. This one is very special. It is in fact the one that's used by all wireless and network access technologies. So what's listed here are just a few examples. Terrestrial microwave operating at about 45 megabits per second maximum. Wi-Fi, well, depending on the version, could be lower, 10 megabits per second, or half of 100 megabits per second. Wider area wireless access, 4G for example, goes up to a few megabits per second. 5G is now tens of megabits per second, okay, with the potential going higher than 100 megabits per second. And satellite radio, yeah, the bandwidth range spans wider with satellite, probably because of where the satellite is exactly and the technologies being implemented on that satellite. It can go from kilobits per second to 45 megabits per second. But one common feature is this: for satellite links, end-to-end delay will always be much longer than all these other wireless link access. Now, as to exactly how long the end-to-end delay is, it really depends on where the satellite is. For geosynchronous satellites, which sit higher above above Earth, the delay will get longer. The low altitude ones being lower, then shorter end-to-end delay. So, radio links, very special. Essentially, we are sending bits through these electromagnetic waves. There are no physical wire, so it's called unguided media. Data can go bidirectional, well, in fact, all directional. Which is a good and a bad thing. If you think about the propagation of these electromagnetic waves, it can be influenced by environmental effects. Having objects around, the objects can obstruct further propagation of the electromagnetic waves. And some objects might reflect, these waves as well. And the waves can be interfering with each other, coming from different sources, or even coming from the same radio source. It's called the multipass effect. So physical media, radio, it's very convenient, but you see the challenge of transmitting signals through these magnetic waves. You see also generally the wireless links, the maximum capacity usually lower than the guided media's capacity. And that takes us to quiz 3. Those who are keen and pick up the hints of my transitional slide, the next topic you see that the quiz 3 follows physical media. Okay, so guys, go find W2 quiz 3 on Slack. Okay, so this is the question. Let me blow up the slide because it's a little bit busy on this. The question is, so I'm using the slide in a busier way. Okay, oopsie. There. Okay, so what I'm showing here are 3 generations of Ethernet cable from 5E to Cat 6 to Cat 6A. But this cat is not honey, that type of cat. This is just cable cat, all right? Okay, what a coincidence. Okay, so I did not stage honey for the purpose, okay? So Ethernet cables are all cats, essentially. And these 3 different generations of Ethernet cables differ, okay, in 2 physical property. The frequency band they're using. Older generation use narrower band and newer generation use wider band, okay? And the physical sheeting also different, okay? The older ones more primitive, the newer ones quite elaborated. So pretty much each twisted pair has plastic, okay, wrap around it. As a result, you see the performances of these 3 generations of cats are being different. So older generation, lower capacity, newer generations, higher capacity. You see also between Cat 6 and Cat 6A, the transmission range differs. Cat 6, 55 meters, Cat 6A, 100 meters, and honey probably a kilometer. Okay, she can meow really, really loud. Okay, so essentially higher frequency range and better shielding gives you better transmission quality. So quiz 3 is asking this. Let me ask you to pretend you are the system admin of an enterprise network as depicted above. So that we're using FTTH to draw in internet data or to send data out to the internet. At the center of the enterprise network is a 10 gigabits per second switch. So Q1 here asks what CAD you would choose for link 3, for cable number 3, and what CAD would you use for cable number 6? And this is a short question. You have 3 minutes to decide which CAD you would use for cable 3 and cable 6. Oh, wow. Okay, we have already, a team. Mao here. Mao here is saying, representing team 4. Cat 6A for... Cat 6A for cable 3. Oh, because it's connected to a NAS, right? And it's longer distance to the central switch. And 5E is enough for a simple 1 gigabit per second PC. There you go. Team 2. And I think Qi-en definitely typed up all the team members, but what team are you? Could you edit the post real quick? Jessica representing team 8. Great. Good. So you guys are picking it up real nicely. Very good. Well done. And let me use a teddy bear here for Santing. Qi-en here gets, let's see, a monkey. How about that? And Jessica and Team A, which one would you like? How about a whale? Okay, it's kind of cute. Jieming, a tracker. Okay, I love trackers. Yo Kwan picked honey to do the transmission cable. Honey is very powerful. I'm sorry. So how about a locomotive, steam engine locomotive? Mindy here. 6A for link 3 and 5E for link 6. Yeah, you guys are all doing the right thing, right? So you are also budget concerned. So for link 6, where you are only connecting to a 1 gigabits per second PC, 5E is plenty. So that's give team 3 a pew, or whatever that pronounces. Okay, Bosch, very good. Kelvin, 6A, and I suppose that's a typo because there's no 6E cable. And Yuhao representing 14, very good. And team 5, very good. Boris on behalf of team 13, wonderful. Hey, very easy, isn't it? Good. So that's just, to get you back in the class so that you stay awake. Let's now move on to the next topic, the core of the internet. It's okay, Calvin. You can still edit it. Okay, so next video. And the sequence of video is going to be a little bit long, 11 and a half minutes. Let's see if you can sustain that long a video. As access network is concluded, let's move on to the next component, the network core, which is a mesh of interconnected routers, as I'm trying to highlight here in red color. So you see a bunch of routers very well connected to each other. By well connected, let's see if you count how many connections this router has to the rest of the internet. 1 here, 2, 3, and 4. 4 connections. Look at this one. How many connections? 1, 2, 3. Look at this one. It's an edge router, all right, but how many connections it has to the rest of the internet? 1, 2, and here, 3, 4. But if you look at a end system, such as this one here, how many connections it has to the internet? Just 1 here, through the Wi-Fi AP. Look at this PC here, only 1. One very clear distinction between these routers to all these end systems is exactly in the connectivity, the number of connections they have to the rest of the internet. For routers, very oftentimes you see more than 2, including 2 connections. For end systems, just 1. And the reason that the routers oftentimes have more connections is because their role are just to transfer data. So it takes us to this very fundamental question. How do we transfer data in such a well-connected mesh network? In general communication network design, very general communication network design, there are 2 major mechanisms. First, circuit switching. Second, packet switching. Idea is quite straightforward. In circuit switching, from the source to the destination, let's build a dedicated circuit, and this circuit is going to be reserved through the entire time of communication, so we could just dump data in, and the performance is guaranteed. And this is the mechanism used by the traditional telephone network. The other technique, packet switching. Instead of allocating resource, creating a dedicated circuit, let's just use the entire link capacity and let's send data out no matter what. But we cut the data such that it's sent 1 chunk at a time. And to call such a chunk of data, we have this term called packet. All right. So it's almost like a package, but packet means also a little package. Okay. So we send data in smaller chunks, but use the entire link capacity. Okay. And to tell you ahead of time, internet or the data network is taking this packet switching approach. All right, now let me elaborate circuit switching a little bit more. This is the familiar network. But this time we see on the network there are two circuits. The red circuit connects this end to this other end. Similarly for the blue end. And to establish such a red circuit, which is also called a call sometimes, and the time it takes to set up such a call or such a circuit is also called the call setup time. Okay. And the reason that I need to mention that term is because that takes time, because resource reservation is required going from one end to another, which means this is the first link on the circuit. We need to reserve a certain amount of bandwidth to guarantee that data gets transmitted without any loss or delay. So you reserve link bandwidth for the call. Data is going to go through a switch. This is the first switch. On the switch, memory, CPU, buffer space will also need to be allocated and reserved. So that is what I meant by switch capacity here, to guarantee that the packet will not experience delay and not experiencing any loss. Similarly for the second hop, for the third hop, fourth hop, fifth, sixth, seventh, and eighth. When all 8 hop link bandwidth switch capacity reservations are done, then you build a circuit. But then you see, as Polly was describing, this circuit here, resources are all dedicated. When data are being passed to, no delay, no loss. Really nice. And we call that circuit-like performance. That implies delay and no loss are guaranteed. Low delay, no loss, guaranteed. Similarly, for the blue circuit. And this is really nice because zoom into this segment. This segment here shared by the blue circuit and the red circuit. The two of them, although packet or data will be going through, but these data will not interfere with each other, not incurring delays to each other, and not collide to each other. No packet drops. These days, where we do online meetings a lot, having live YouTube channels a lot, we'd really like to have this circuit-like performance. This way, we don't have to worry that the internet is going to go bad and the live stream is going to break at some point. Nice. Because for certain applications, we do need this type of quality of service. But you see, establishing the red circuit, we need 8 hops, and each hop takes some time to reserve resource. So there's quite a bit of call setup time involved. This is the downside of circuit switching. Another downside is this. The way we are allocating or reserving resources over the entire path from the two ends of data communication is more. We divide the link bandwidth into smaller pieces. We divide the switch capacity also into smaller pieces. And once we do that, we allocate individual pieces or combinations of pieces to an individual circuit or individual call. But once you do that, if there are no data being sent between the two ends, that piece of resource will then be idle. If you think about it, in a way, it's a waste of resource. If the two of them ask for resource and a call established, but they're sitting doing nothing. So not very good utilization of resource. So this is the second disadvantage of doing circuit switching. Now, speaking on dividing link capacity into pieces, there are multiple ways of doing that. First one is called frequency division, the other time division. This is the second time we see the term F, D, and Where did we see this? Yeah, cable modem. We divide cable modem capacity. We divide the cable network link capacity into what? Pieces by the frequency band. This is a very different flavor. Okay, it's dividing the link by the time. Let me illustrate. The example on the top is doing FDM, where we divide the entire frequency band there to 4 users in equal division. So, full frequency band, 1/4 to the blue user, 1/4 to the green user, to the yellow user, and the pink user. TDM works this way. Instead of dividing the frequency dimension, that's divide, okay, in the time dimension. So with these time slots, we allocate the time slots in a rotating fashion to the 4 users like this. Blue, green, yellow, pink, blue, green, yellow, pink. Yeah, it's rhythmic. That is exactly how TDM works. With a good rhythm, with well-synchronized time, the 4 users can send data one after another. Very orderly. If we have more than 4 users, how do we do that? You see, we could further refine the division into, for example, A parts. That way we can accommodate how many users? A users. Similarly for TDM. All right, so let's pause here a little bit because Bianjing is asking a question. So if there's n users to be connected, it would need circuits to make them connect. Oh, that's a very good question. If each one of these user pairs needs to be guaranteed a circuit, yes. But usually there will be some period of time, a particular pair not being used. So the allocation here or the division there is a little bit more dynamic. Okay, I hope that answers the question. If you want to make sure that there is a circuit for every pair, yes, Bianjing, you're right. But in practice, it's a little bit more dynamic depending on how many active pairs there are looking for circuits. Now the last bit of circuit switching. To make sure you pick up circuit switching and how it works. Let's see if we can work out this problem together. The question asked is, how long does it take to send a file, this big, from A to B over a circuit switch network? And in this network, all the links have the same capacity, 1.536 megabits per second. And each link is divided to 24 parts using TDM. And meaning that circuit between A and B only gets 1 slot. And the presumption is that to establish the end-to-end circuit between A and B, it takes this much time. Alright, so how long does it take entirely to send the whole file through? Let's work on it. All right. So let's do some calculation. All right. Let's see whether Polly is able to do this. Okay, come back. There. The question is to send a big file from A to B. Okay, and there's a link between A and B running at this bit rate. But the link is using TDM and it's already configured to do it this way. So essentially each pair of users gets 1/24th of the total bandwidth. So the bandwidth allocated to A and B is only 1.536 megabits per second divided by 24. Okay, now, excuse me, I need a calculator here. Let's say 1 536 kbps divided by 24. Oh, that gives me 64 kbps. So this is the link rate between A and B. And I do have 640 k bits to send. Let's divide that by 64 kbps. It's obvious we need 10 seconds to send the data. But recall, in order to send data through circuit switch network, we need to establish the circuit as well. And given that there's a 500 millisecond delay to do that, the overall time to send the file from the very beginning to the end will be 10.5 seconds. All right, so did you come to the same conclusion? I hope so. With that said, we can now move on to the next part. If I can get my cursor back. Yeah, there we go. Yeah, to packet switching. Now, the video here is also a little bit long, but let's just go over the introduction. That takes about 5 minutes, and then we'll take a break. Now, let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets. And as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay, this being small, this being large, to send a packet, very small. This is one advantage. And then think about this, if you get two users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching when B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource as a result. B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle waste there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send, so the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the keyword. Delay here to transmit the packet is short, but there could potentially be way that is a little bit uncertainly long. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here. This one is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything. So you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there passing packets is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these, L divided by R, every hop, every router. All right, so that was packet switching. You see there's a big difference between the two mechanisms. And let's continue after the break. So let's take a 10 minutes break. So we'll return at 11:22. And feel free to type up questions in the meantime. Jiao was asking, yeah, exactly. To transmit the 640 bits per 640 kilobits of the file, the physical amount of time we use is really this much. Okay, but they are spread out over 10 seconds. So physical time the bits are being transmitted down the cable is exactly 10 over 24 seconds. But in order for B to receive data, B needs to wait for 10 seconds. Okay. So the time we're calculating here is the user experience time. All right, so break. Let me go back to the opening side like this. Great. Don't worry, I'm just making some modifications. It's not like the stream is going bad. Okay. I hope you don't mind that I edit the OBS scenes online like this. It'll just take maybe a minute or two. All right, it's 11:20. Let's continue on. But before we do, there are a couple questions right before the break. One is from Ming Hong, Luo Ming Hong, I think. The question was, is store and for happening between switches? Yes, every pair of nodes. Okay, between switches, between end system to switch or switch to end system. So essentially you send packets to the next hop, next node. This next node will need to store it, look into the packet before this node knows where to forward further. So you store and forward, and there's a delay involved in doing that store and forward. And that is actually a very good question Ming Hong asked. I think that partly triggered Yunqi to ask. Does store forward also happen in circuit switch network? You know what? It does. This is a very good question. Okay, but the way that circuit switching network does it is only per bit, because you still need to grab a bit before forwarding further. Okay, but grabbing of a bit, time very small, and there's no need of looking into the content of a bit to decide where to forward next, because it's already set up. Okay, the bit as it arrives, we know already where to forward. Okay. Oh, there's another question here. Okay, good that I go over the questions on the YouTube chat. Does frequency of a cable mean the bandwidth of this cable? You know what? Zoe, it does. It does. Usually higher frequency bands, it's a little bit easier to extract what we have modulated, because the signals is usually a little bit more robust for modulation and extraction. Lower frequencies is a little bit harder, and yeah, that's pretty much. Lower frequency signals are also more sensitive to noises. Okay, so usually higher frequency band implies also a higher bit rate. Okay, so there's a second part of Zewe's question. If so, how does its capacity exceed its frequency? Okay, so I have to think about this. Okay, it might have something to do with the way you ask the question. Yeah, I think the problem started from the first part, the frequency of the cable. So I think you are asking about quiz 3, right? So Cat 5e, Cat 6, and Cat 6a, I say frequency of 5e is 100 megabits, 100 megahertz. Okay. But what I meant there is more the frequency band. Okay. The wider the band, the higher the frequency, usually get better. So it's not just the frequency, but also the band there. The Ethernet signals all run on the same frequency, 2.4 gigahertz, in fact. Okay. But there's a slight differences, but within hundreds of megabits. Within hundreds of megahertz. Okay, band there. In the central frequency of 2.4 gigahertz. Okay. I hope that's clear, Zoe. Ethernet signals, wait, is it on? No, not exactly. Sorry. Hey, Zoe, I was mistaken. I was talking about Wi-Fi. Wi-Fi is on 2.4 gigahertz. Okay. Ethernet, I actually don't recall exactly what frequency band. But usually there's a central frequency band, and then there's a range. Okay, you modulate the bits on. So 5e there, narrower, and 6a there, wider. Okay. Oh, Yunqi just typed up something and then extracted it. It's okay. So when you find out the way, a right way to ask it, okay, feel free. So Zoe, for your question, yeah, let me look things up so that I can say this in a correct way. Okay, I'm not very comfortable about the central frequency the Ethernet, the wire Ethernet is using. So I'll look it up and make sure that I get things right. All right, so thank you for the questions. Good that you guys are picking things up. All right, now let's move on and talk about packet switching. But this time, let's talk about the downside of packet switching. So here, let me illustrate the store and forward effect to the end-to-end delay. So consider this scenario. The source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long, and the link bandwidth is R BPS. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1L divided by R for this hopping. Because this guy, to send it out, it requires L divided by R. This router here receiving it waits until O is received, and then what? Send it out again. That's another L divided by R. So if L is 7.5 megabits per second, R is 1.5. You see each hop, 5 seconds. 2 hops in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This side is to illustrate congestion. The scenario is A and B, 2 users generating packets. A generating A generating green packets, and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, everything goes rotating rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay, so on packet switch network or on the data network internet, packet kind of, multiplex to each other randomly, spontaneously, depending on how they're generated. Now let me draw your attention here. The router. You see packets encase the outgoing link, bandwidth small. And incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chances very high, A and B, if both of them actively generating lots of packets, the packets will have to wait here in the queue before they get the link queues. And if there's not enough space here for the queue, the next one, the green one coming here, will need to be dropped. But there's no memory space to hold. And those packets waiting in the queue, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get. All right. So that was the downside of packet switching. In the next 20 to 30 minutes, we'll do this. More comparison of circuit switching to packet switching. I see you guys are asking questions already, thinking, if packet switching worked this way, how come, right? We don't have that issue in circuit switching and things like that. So that's, use an example to compare circuit switching, packet switching, and then I give quiz 4 that you guys can think as a team more about circuit switching versus packet switching. Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users and each of these users are not exactly very active, sending short messages only each time. All right, so scenario is very simple. Okay, we do have a network of end users and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of the time active. in a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits, so we can only allow 10 users, okay, 10 circuits. But in packet switching, you see, the users are only active at 10% of time. Consider this scenario. If we have 35 users, right, the only situation that these 35 users who will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the user needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%. Okay, let's now work out and find out how 0.004 is calculated. I suppose you are all good and pay attention to the probability class. And now let's move on to quiz 4. Poisson distribution, yes, independent. But hey, Yunqi, no, we're not working that out. So that belongs to the probability class, all right? For probability class, it's probably a exercise or a homework assignment, a rather straightforward one. Let's move back to talk about circuit switching and packet switching. So quiz 4, okay, is saying this. We now know circuit switching is the mechanism that reserves resource before we send data out. Okay, so that data do not need to compete with each other. Okay, it's a little bit like establishing pipelines to transmit water. Okay, so from the bucket at the building's rooftop down to the household use, there's no congestion. Okay, but packet switching, there's no delay. Oh wow, okay. Okay, packet switching is more that you package the data. Okay, and you package in a way that they are all kind of small, so we call them packets. So small package is called packet. Okay, so we put them into small messages, small packets, and send them out to mix with other packages or other messages from other users. Okay, and have them kind of squeeze themselves through the network. So it will be a little bit more like we carrying buckets and taking waters from one place to another. Okay, it would be more like having multiple people and using buckets to transport water, something like that. And if there's a person standing in a way where there are 2 incoming buckets of water, then this person gets busy. So Q1 here for quiz number 4 asks, which principle do you think the car network follows? Okay, so the car network is the vehicular network here, right? So your parents probably drive you from Kaohsiung to the dorm when you first register to NTU. Yeah, what kind of principle do you think the car transportation or human transportation network is designed? Okay. And what about the train network? Okay, do you like trains? Okay, Polly loves train. Hey, we actually need to establish these railways first, right? And then we can have the train cars running on them. So this type of people transportation system, this type of car transportation system, Oh, is it more circuit switching like or packet switching like? Oh, and circuit switching versus packet switching, which one do you like better? For Q3, what's more important is tell why. Now, quiz 4 here, you can probably tell that it's a long question. This is the type of question that Polly likes that the team find each other online somewhere and have a good discussion. You'll be given more time. So you have 10 minutes time, in fact. Okay, so take your time. I see that then we move to the Slack space because we do have some very aggressive students. So Boris representing Team 13. Yeah, there are already some answers for it. Okay, but let's go over these after the other teams finish discussion and see how they think. Okay, car network is, how they think train network is, and packet switching, circuit switching, which one you like better and why. Oh, by the way, if you think car network or train network is one way or another, try if you can explain why you think so. So it would you see that of course we can guess, right, and hope that there is like a one answer for it. You see that there are actually multiple answers for each of the Qs. So what's more important is you justify why you say it's packet switching, why you say it's circuit switching. Boris, it's okay. It's okay. I love that. Be careful having too much coffee. I sometimes, drink too much coffee. And by the way, aggressive is a good thing. Passive can sometimes be also a good thing. Okay, just one more minute. Interesting. All right, so I can see from all the teams. Okay, so team 13 says the car network is a little bit more like packet switching, right? Because they can take turns and go on different routes. And they can be congested, right, at a certain intersection. But trains, once the rails are in place, they are restricted to go on that route. And the bandwidth is somewhat reserved. And Team 13 prefer packet switching because it's a more efficient use of the resource. Efficient will matter a lot when there are many users surfing the internet. Yeah, because when the way we surf the internet is request a page and wait, right? Until you see something interesting, you click again. So it's not more like continuous stream. That was exactly what the internet engineers were thinking, because the internet is designed more packet switching way. But telephone network, right? We always, speak with the grandparents, and the grandparents couldn't seem to hang up. It's a continuous stream for some time. Yeah, that I think is perfect for circuit switching, such as what Team 2. Okay, Yunqi was saying, if the stability is required, then CS. Okay, but if the speed or utilization of the resource, okay, if maximizing the utilization of the resource is required, then PS. Okay. Yeah, I think many of you prefer packet switching, right? Because to send a page, you use the full bandwidth faster. Okay. Unlike circuit switching, especially when you have 24 other connections sharing the full bandwidth, right? You only get 1/24 of it. It actually takes longer, but stable. I think Team 15, similar. Use the resource to the fullest. Nice. Less waste. 21st century, the key word is certainly economical. Yeah, efficiency, definitely. Similarly, Team 4, efficiency. Mindy here, flexibility as well. Yeah, so lowering the opportunities, lowering the chances of idling. Team 10 here, prefer packet switching since we hate waiting. All right, sure. Yeah, short delay, as short as possible. And the best will be what? Stable and yet fast, isn't it? Can we design the core, internet core that works with short delay and fast? Challenging, isn't it? Hey, but think again. I think internet engineers come up with a solution. To address sending multimedia content, sending videos, such that the delay is short. And hey, is the video session right now stable? It is. Okay, so in chapter 2, you'll see. Okay, I think Ziwei, yeah, it's more efficient. Good. This is very good discussion. Let's move on to wrap up. Comparison of CS and PS. After the discussion trying to solve the quiz, what do you think? packet switching versus circuit switching. Do you think packet switching is the slam dunk winner? Is data network internet's way always gonna win? Probably not always, isn't it? It's great for short bursty data, right? Short amount of time but sending lots of data, because it promotes maximum resource sharing, and it's quite simple, no code setup either. But on the other hand, we do have congestion. Packet delay might be unexpected long, and probably worse, there could be packet losses. And so you need additional protocols, because of the way the very low level packet forwardings are designed. So we probably need extra mechanism at the higher layer to ensure data can be transferred in a reliable way if it's necessary. And what if we want to do some level of a guarantee, for example, to do video streaming? Can we achieve circuit-like behavior with packet switching philosophy at a very low level? Can we do bandwidth guarantee? Well, people have been thinking about it, and this is still a problem that's not quite yet solved. And this is covered in Chapter 9, the Multimedia Networking chapter, later on in the textbook. And we unfortunately won't have time to cover this semester. And that takes us to the last part. Remember Boris, Chen Tao was asking, why, I mean, we can just pipeline things, right? We can take bits and then pipeline the bits out straight. Okay, so take a look at how we can pipeline packets, okay? And you'll see why we will experience delay in a packet switch network to do store and forward. The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages? Right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have 2 hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds, and because there are 3 hops, so this time store 5 seconds for, store 5 seconds for, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 millisecond, and only 3 milliseconds until the destination receives the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You are trying to do also streamlining here, except that the unit of streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. The overall delay in the end is what? 5002 milliseconds, only 5.002 seconds. If you recall earlier, if we send 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets. And why do we need to store packets first before forwarding it, right? This is one of the reasons that we still need to form packets. Why we cannot just streamline the bits. The reason has something to do with how the routers is working. So inside the router, there are 2 key functionalities, and there are 2 of these. First is routing. So there's some sort of algorithms there. The routers, given the graph of the network, computes the shortest route. At the end of it, we generate a routing table like this, a forwarding table like this. And the way we look up this table is by matching the destination address, of the packet. And so if a packet comes into a router, inside the router takes the destination address in the packet and look up this table. If there's a matching entry, the router discover what is the next router to forward to, what is the right direction to pass this packet further. You see, router what? Oftentimes well connected to other routers on the internet. So this router here could have multiple ways of passing the packets further. Unlike the very simple scenario there, each router has only one outgoing link, right? So it's no longer that intuitive why packets need to be stored and then forward. Now you see, packets need to be stored here. And then the router can look up this field and match this entry and then discover, okay, this packet is supposed to go out on network interface 2, this direction, to this router next. Similarly, this router needs to store the packet entirely, and then it can look at the header, this particular field, destination address, and find out in its own routing table which router next to forward the packet. Yeah, it's exactly because of the forwarding functionality that's required to pass data around over a packet switch network like internet. So, on packet switch network, we store packet before we forward it. So, forwarding here is to move packets to routers all the way from the source, eventually reaching the destination. We'll definitely tell you more as we come to chapter 5. Okay. So in datagram network or in data network, the way it works is let's receive a packet entirely, and look up the destination address to determine which is the next hop. And so you see, if the routing table change, if the graph change, routing table would change. When the routing table change, when the forwarding table change, the subsequent packets might be following a slightly different path to the destination. Okay? So the routes, packet traverse might change in a session, in a data stream session. So the analogy here is that packet switch network is a little bit more like the regular car network. Okay, if we are driving a car, a lot of times, to find out the next segment, okay, which road segments we should go on, we might actually stop and pause and ask someone for this destination, for direction, or park to the side and then look up Google Map to find out which is the next segment. And actually in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID. And one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. Two different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If we are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued. And they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tag, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching. And that concludes today. So we are a little bit early, but it's okay. Go get lunch. If you have follow-up questions, feel free to type them up on YouTube channel or the Slack. Ask us anything. I'm gonna leave the stream on for 4 more minutes until it's really time. to call it off. But feel free to go and grab lunch. There you go. So Yunqi is asking a question, right? So then in this case, we make the packets as small as possible. Is there any drawback preventing us from doing that? Yes, there is. There is an issue with small packets. You see that, as you heard just in the last video, the packet will need to arrive, right? And there's this packet header part that the router need to examine to extract the destination address before the router can decide which is the next router to pass the packet further. So that implies in a packet there's this header part and there's the...
I'm not sure I understand.
Okay, thank you, Siri. Sorry, I accidentally wake the Siri up. Oh, by the way, my Siri is a male voice. So a packet, there's header part, and there's the payload part, the part that contains the real data. So in the header part, what's contained there are important control information. For example, destination address. So for example, size of the packet. For example, priority of the packet. And there could carry some additional information, for example, the checksum of the data. So these various information in the header are to allow the receiving end to check and decide what to do next. Okay, so destination is to decide where to forward it further. The checksum is for the receiver to decide maybe there's some bit errors in the data. It's probably better that we discard this one because it's not right anyway. It's not correct anyway. Why don't we send the request back to the sender and ask for a better copy, a correct copy? Okay, so there's this header part that contains all sorts of control information, not quite the real data. So in a packet, there's a control part and there's a real data part. But you see, the purpose of the communication is to send as many data as possible. Okay, so a smaller packet means the proportion of data for all the bits we need to send is lower. Okay, so there's a special term being used there. It's called throughput or good put. So these are to measure the actual amount of data, actual number of bits of data being transmitted through. Okay, so smaller packet, you have a lower good put there. Okay, the proportion of effective data being sent, lower. If you think about it, it's not very good utilization of the network capacity either. Okay, I hope that answered your question, Yunqi. And oh, Liangyu, are all the assignments on the class website correct? I noticed some information on the website is from last year. I think you probably meant PA or quiz. Let me think. Okay, Liangyu, help me here. Do you mean the PA? Okay. Yeah, it could be. So could you post on Slack, ask us anything, and so that we could clear. Yeah. So there might be things that I need to update. Okay, so if you post anything you see weird there, then I'll be able to address and update the PDF. Okay, so yeah, Liangyu, can you help me with that? So exactly which PDF and where you think is not quite correct? Okay. I mean, of course, I can go to the PAs and check them through. I'll try to do that maybe this weekend. But if you see anything weird, just let me know. If a queue line has no space to store packet, how to determine? Oh, okay, that's a very good question, Coach. Yeah, there are different policies one can implement. Okay, so when the packets arrive to a router, there's a buffer space. That buffer space is called a queue as well, because packets will arrive and they will be queued up in order. Okay, and there are different dropping policies. Typically, we drop from the tail. So the one arriving to a full queue, there's no space. Instead of kicking one of these guys out, the one arriving late got kicked out. That's the drop tail policy. And that is the policy that's the most commonly implemented, not just in the computer world, but also the human world, because you're late. So you see, again, timing is important. So aggressive is not a bad thing at all. But there are other policies. For example, you can random drop. So there's a new packet arriving. The router can actually choose to drop one of the packets in the existing queue randomly. In fact, there's a version of TCP that works with a random dropping queue. Oh, by the way, TCP, I'm jumping ahead. It's a topic in chapter 3 when we talk about the transport layer. Yeah, so 博智, I hope that satisfies your curiosity a little bit more. And if you don't mind, we'll definitely talk about this in chapter 4 when we're talking about forwarding of the packets. Okay, because we will be talking about the architecture of a router and talk about queue, how you implement a queue. And so there are two policies that one need to implement there. One is called the scheduling policy. When a packet arrives to a vacant queue, so meaning queues having some space, it's not necessary that we insert the packet to the tail of the queue. You can actually insert it randomly into the queue, or to the front of the queue, or to another queue that's at the higher priority. So that's the scheduling policy. And then, of course, another policy we implement is the dropping policy. If a packet arrives with a full queue, okay, so which packet gets dropped next? Let's see. Sharpie small, but not too small. Exactly, Yanjun. Yeah, I used to have like an exam question, but it was it was a long time ago. You guys get to calculate. So I give, for example, the header size being H, data size being D, okay, and the link capacity being that. What is the best balance to reach the highest utilization? So one can actually calculate. Liang, got it? I'll check it later. Yeah, so please do, Liang Yu. I know for sure that towards PA 7 and 8, because I actually refer to Google documents, and you see, I refer to Golan documents, and you see that Golan is an open source effort. It's still expanding. So the documents, the lines that I refer to has been changed. So I need to update that. But the trouble there is that I update it now, but during the semester, those documents can be changed further. Okay, so I'll need to come up with a way of being a little bit more general, okay, referring to it. So Liang Yu, if you see anything that's a little bit weird, in fact, this is a general request to all students in the class. If you see anything weird, please feel free to let Polly know. It's not offensive at all. Okay. Polly is a little special this way. Okay, I'm also a little bit of a perfectionist. Okay, I feel uncomfortable having errors, but I wish that there are 48 hours a day. Eximan. So if the packet is dropped, the receiver would ask the sender to send again. Good, very good question. Okay, it really depends on the mechanism. Okay, routers, some of the routers might be implemented so that they ask the previous router to retransmit. This, in chapter 5, you will hear nowadays the routing is done in a very flexible way. Okay, not just one algorithm. In fact, the system admin, the network admin can actually configure things for a specific router to do this. For example, the router immediately connected to a wireless edge, because wireless packets oftentimes having bit errors. If you send packets with errors out on the internet, it causes lots of problems and generate a lot more traffic than just the router right next to the wireless network simply asking for retransmission. Yeah. So one can actually do that. But generally, most of the routers on the internet, if we see a bad packet, I don't know, does router drop packets? Because, no, sorry. Routers don't drop packet at all if they are bad. But a switch, Ethernet switch, okay, I can pull it out. I just installed it, but I don't know if you can see it. It's a little black box from the link. Only 5 ports, 1 for incoming link and 5 for the split. So that switch, I believe that it does packet drop in case the checksum didn't pass. Okay, Yanjun is asking the same question. If the packet gets dropped, the receiver asks the sender to send again. Yeah, so routers don't really do that, although it's possible with the very flexible software-defined networking that many of the big companies are using today. I don't know if NTU is using it. I don't think so, because our computing center are not exactly capable of doing that yet. But if we are speaking end-to-end from one end system to another end system sending data, if the receiver check and see that the checksum and data don't match, receiver sends a message to sender and asks for retransmission. So this is exactly the very basic design in TCP, okay, the protocol that I mentioned just a little bit earlier. Okay, that's again in chapter 3. Great, sounds like you guys all can't wait to get into chapter 2 and chapter 3 and chapter 4 and chapter 5. Okay, but we do need to go. All right, so that's call it a day. Further questions, feel free to post on Slack. Okay, and bye.